Now we're going to talk about extrinsic factors. Those are referring to external conditions that can prevent food spoilage. Some of the factors are temperature, relative humidity, and also gaseous composition. The first one is temperature. Temperature storage is the most important factor to ensure food safety. I think I touched a little bit when I first introduced the food microbiology topic. We talk about temperature danger zone. We have to keep cold food cold and also keep hot food hot. So the safest temperature range should be above 60 degrees Celsius because bacteria are destroyed in such a hot temperature, or we should keep it cold below 5 degrees Celsius, meaning that we need to refrigerate our food, or better, we can frozen the food so that bacteria won't grow. Bacteria is still there, it is not destroyed. However, we inactivate the enzyme of the bacteria so that it cannot perform metabolic reaction for them to grow. However, you have to bear in mind is that refrigerated food can also gone bad. Why is that the case? Let me explain you in the following slide. Based on temperature, bacteria can be divided into its optimal growth. There are at least 4 different types of bacteria if we want to divide it into its optimum temperature growth. The first one is sclerophile, meaning it has the ability to grow below 0 degrees Celsius. The optimum growth temperature of this group of bacteria is around 10 to 15 degrees Celsius. It is not very common for foodborne pathogen or spoilage microorganism categorized in this sclerophile group. The second group is psychotrophic. These actually are mesophiles that can grow in refrigerated temperature. So let's first visit what is mesophile. Mesophile are bacteria that have optimum growth temperature of 37 degrees Celsius. Actually, most bacteria are in this group, mesophiles. Optimum growth temperature of 37 degrees Celsius. Some of the examples of mesophile bacteria are Salmonella, E. coli, Listeria monocytogenes, Pseudomonas, and Staphylococcus aureus. Now, let's revisit psychotrophic. Those are mesophile that can stand refrigerated temperature. Refrigerated temperature is around 4 to 10 degrees Celsius. Some of the examples are Listeria monocytogenes and also Pseudomonas. These type of bacteria usually cause spoilage in milk. The last group of bacteria is thermophile. Thermo referring to heat, meaning that this type of bacteria love heat. Thermophile. Philes mean love. They are able to grow above 55 degrees Celsius. Some of the examples of this type of bacteria are Clostridium, Streptococcus, and also Lactobacillus. Food that are refrigerated only can stand for a definite number of days. For example, milk, you can only store meat in a couple days. After that, spoilage microorganisms can still grow, such as Listeria monocytogenes and Pseudomonas, which cause the milk to be spoiled. Technically, by refrigerating food, we can only extend the shelf life of the food to avoid the growth of most spoilage microorganisms, which are mesophiles. Another thing I want you to take note is that it's always a range for microbial temperature growth. What makes a difference between all those groups is actually the optimal growth of the microbes: sclerophile, mesophile, thermophile, and also hyperthermophiles. So the most common, before I talk about psychotrophic, meaning cold temperature usually below 4 degrees Celsius, refrigerated temperature. If we want to talk about high temperature, meaning we want to inactivate, we want to kill the microbe using temperature, there are several concepts that I want you to know. The first one is D value, the second one is F value, and then the third one is Z value. So what are those? So before I explain all the terms, I just want to explain to you about the concept. So say we start with a number of initial microbial population here. So as you apply heat, you want to kill the microbes, the number of microbes will decrease across time. So the dot here basically just referring to number of microbes that are decreasing across time if you pick the sample at certain time interval. So when you plot this diagram here, what you can obtain is actually the d-value, the inverse slope of this graph. The d-value refers to the time that is required to reduce bacterial population by 1 log at a given temperature, at a constant temperature, so at a single temperature. So when you want to plot the graph, it has to be log transform microbial count. Then you can only obtain the inverse of slope to get the d-value. So remember, d-value, the unit is time. Time for what? Time that is required to reduce bacterial population by 1 log at a given temperature. So in order to express the d-value, it is usually written like this. D, the temperature, what is the temperature that you are concerning about, and then the time that it takes, 3 minutes. So imagine if I increase the cooking temperature maybe to 120 degrees Celsius. Do you think the time here will decrease or increase? Well, if you increase the cooking temperature to 120 degrees Celsius, of course the time that it takes to reduce the bacterial population will decrease. Maybe it can reduce to 0.3 minutes. Vice versa, if you decrease the cooking temperature, maybe 80 degrees Celsius instead of 100 degrees Celsius, then the d-value, the time that it takes to reduce the bacterial population will increase. Maybe instead of taking 3 minutes at 100 degrees Celsius, at 80 degrees Celsius, it will maybe take like 30 minutes. So I just want you to see the trend of the d-value and the temperature. Another concept is f-value. So f-value is also referring to time. The difference is that it is multiple d-values. So in food microbiology, especially food safety, we are concerning about f0, which is the standard value that is used for commercial sterilization. f0 equals to 12d, meaning 12 times d. So in commercial sterilization, the f0 equals to 2.52 minutes. So if you divide 2.52 minutes to divide it by 12, you will obtain a single d-value at this temperature equals to 0.21 minutes. So just remember that this temperature, 121 degrees Celsius, is a temperature used for commercial sterilization. Another important term that I want to explain is z-value. So what is z-value? Z-value is actually the temperature required for a log change of d-value. So let me explain here. So before I explain with you d-value, so the time required to reduce a bacterial population by 1 log at a constant temperature. Say you want to test not only one single temperature, but you want to test maybe 3 different temperature or 5 different temperature, because you want to assess like which temperature and which time work best for your processing, for example. So when you have multiple temperature, then you will obtain multiple d-value, right? So what you're gonna do is that whatever result that you got from the d-value, you will convert it into log. And then what you're gonna do is that you plot the number in the y-axis, and then x-axis is the temperature that you use. So a log change of d, which is the inverse slope, you actually when you calculate it, you will obtain the z-value. So basically, z-value is that the temperature required for a log change of d-value. For example, if you think that you want to increase the time of the cooking, then you will also refer to Z value, how much temperature you need to change to achieve that cooking time, or vice versa. If you want to reduce the cooking time, how much temperature you need to increase to reduce the cooking time. So basically, that's the concept of D, Z, and F value. The next extrinsic factor is relative humidity. Well, relative humidity really closely related with water activity. The difference is that water activity is talking about the food itself, the water that's available in the food. However, relative humidity is talking about water available in the environment of the food. So I'm giving you here a quick relationship between those two components. Low water activity plus high relative humidity will result in water gain. So meaning that the food will gain the moisture, water, from the high relative humidity environment. Vice versa, if the food is high water activity combined with low relative humidity, that indicate water loss, meaning that the high water activity food will eventually lose water to low relative humidity because it will reach equilibrium. So this figure I obtained from a journal that I cited here really best represent the relationship between moisture content, relative humidity, and also the temperature. So the take-home message from this is that you can see that the higher the relative humidity, most microbes will grow in this region. Bacteria, fungi, and even insects, although insect is not part of the microorganism. As the relative humidity goes down, then you can see that how much bacteria will thrive, and at last, low relative humidity will inhibit microbes and insects to not grow. So just make sure that you understand the basic concept here, which also similar to water activity, where higher than 0.91 most bacteria will grow, and then as the water activity goes down, you can see only a small portion, only a selective microorganism that can survive in that dry condition will grow. So in this chart here is basically just for your information. I'm just sharing this kind of like decision chart about humidity condition of a storage condition. So I will leave you to read it by yourself, kind of like go through all the arrow and then try to think about what kind of food belong to this kind of I would say cases indicated by the arrow here. The last factor is modified atmosphere packaging, or in short MAPS. The principle of this is that we want to reduce the presence of oxygen because oxygen can promote spoilage microbial growth. Remember, most microorganisms need oxygen to grow except for a few. And also, we want to limit metabolic reactions such as lipid oxidation that will cause rancidity or browning or ripening. Usually, high-fat products such as potato chips here, we want to reduce the oxygen because we want to limit the lipid oxidation. That's why for the packaging of a chips like this one, you will think that the manufacturer tried to lie to you because they only put half of the chips in the bag, the rest is air. Well, it's actually for a good reason. It's not intentional. So usually the composition of the gases that is used to modify the atmospheric condition is nitrogen, carbon dioxide, and also argon. The only possible risk for MAPS packaging is the growth of anaerobic or facultative anaerobic bacteria such as Clostridium botulinum, because they love low concentration level, or sometimes they don't need concentrated oxygen for them to grow. So it's a risk for MAPS packaging because the atmospheric condition has been altered in such a way that the amount of oxygen is reduced. These are other food that can be packed using MAPS packaging to improve its quality as well as its microbial safety. Okay, To summarize, I have covered intrinsic factor as well as extrinsic factor. So how can these be used in hurdle concept? So basically, when you think about a food, we want to think how we can extend the shelf life of the food. So for example, fresh milk, how we want to extend the shelf life of fresh milk. One thing we can do to apply heat, which is specifically called for milk, is pasteurization. Raw milk, we know that it rich in nutrient and a lot of microbes can grow in milk very rapidly due to high nutrient content. So we pretty much apply pasteurization, apply heat to the milk to reduce spoilage microorganism as well as pathogenic microorganism. However, pasteurization is not sterilization. Pasteurization is only reach to sometimes 72 degrees Celsius. It's not commercialization where it reach even higher temperature, 121 degrees Celsius. So pasteurized milk still need to be refrigerated to control the microbial growth that can survive pasteurization. So that's why pasteurized milk, we will refrigerate it for a certain period of time depending on the expiration date before we can discard it because it is unfit for consumption. The next one is fruit jam. In general, fruit jam is high in sugar. So if we try to understand the process of making a fruit jam, one of the first thing that the manufacturer will do is cook the fruits, want to form a mushy, a jammy flavor, but and also indirectly, the cooking will actually kill the spoilage microorganism on fruits because we know that fruits are perishable food products. And then you want a sweet taste to it. We add a high amount of sugar. Basically, the purpose is to reduce the water activity of the jam because sugar will bind with the water available in that jam environment. Sometimes some recipe also add lime so that the pH of the jam will be reduced. And lastly, in terms of packaging, to avoid the presence of oxygen, usually the jam will be packed in a jar or in any vacuum sealed packaging to make sure the shelf life of the fruit jam even can stay long. Another example that I want to share with you is fresh cut meat. Matte packaging can also be used to extend the shelf life of the meat. However, if we want to make sure that the shelf life can stay even longer, of course we want to add more barrier for spoilage microorganism to grow on meat. So on top of matte packaging, we also add an antimicrobial pad here to add another barrier. And once you packet it, of course, you want to store it in a refrigerated temperature because you don't want the temperature to raise to for example, ambient temperature to promote microbial growth. So remember, most bacteria prefer ambient temperature or optimal growth of 37 degrees Celsius for them to grow. And of course, along with refrigeration, you want to also control the relative humidity to make sure that the freshness of the meat is preserved. The last example is fresh cut vegetables. Matte packaging can also be used. On top of that, you can also store it in refrigeration. Is there any other barrier that you can think of? If it is, you can jot it down. Try to think of other food that you think that when you apply extrinsic and intrinsic factor, you can extend the shelf life of that particular food. So to summarize everything, in this week lecture, we have covered microbial growth curve. Remember how to calculate using the information that you have. For example, if you have the doubling time, what are the total bacterial population after a given time. You also have been exposed with intrinsic parameters. What are they and how they can inhibit microbial growth, as well as extrinsic parameters. So, okay, with that, Please complete the short task that I've given you to record your attendance. And if you have any question, please let me know via WhatsApp. If I cannot answer it immediately, I will try to respond it as soon as possible. Okay? Thank you. Have a great week ahead.